Hello, my name is Nick O'Brien. My research focuses on gaining insight into Holocene glacial variability based on seismic imaging of sedimentary packages in Icy Bay, Alaska. Icy Bay is a body of water located on the southeastern coast of Alaska and was formed by the erosive effects of the Tyndall, Yahtzee, and Guyot glaciers. Icy Bay is also located on the Yakutat microplate, which can be found between the Pacific and North American plates. The interaction between the Yakutat plate and the North American plate grades from transform to collision to subduction, making the region tectonically complex. This tectonic activity resulted in the formation of the high-relief coastal Chugach-St. Elias mountain ranges, which, in combination with glacial activity, produces voluminous quantities of glacial marine sediment. Icy Bay is also projected to be coincident with the Pamplona Fault Zone and the Malaspina Fault. In August 2016, a coalition of geoscientists collected multi-channel seismic data in and around the bay. 47 seismic lines were collected in the bay itself, and they are mapped here in Figure 2. Two different streamer configurations were used for this data collection, and their geometries are detailed here in Figure 3. Once this data had been collected, processing was done with two pieces of software, the Paradigm software suite and Python. The raw GPS data for these seismic lines was in a format unusable by Paradigm, so we developed scripts in Python to put them in the proper format. Once this was done, the raw shot data and the formatted GPS data could be imported into Paradigm and used to generate brute stacks. These brute stacks gave us preliminary insight into these seismic lines and allowed us to perform other jobs on them, create velocity with depth models, and produce the final seismic sections. Examples of these final seismic sections can be seen in Figures 5 through 9. In all of the following sections, the green lines correspond to the water bottom. The black lines correspond to horizon 2, and the blue lines correspond to multiples. Figure 5 details line 1698, found here. 1698 can be found inside of an orange L-shaped region enclosed on the base map. This region is characterized by a relatively flat water bottom underlain by rapidly changing topography. Figure 6 details line 1685, found here. We observed many sediment-filled basins in this area, and this was an example of one of them. In the vicinity of the green star, this basin sedimentation exhibits strong reflection layering just below the water surface, and in the vicinity of the white star exhibits chaotically distributed reflectors. Figure 7 details line 1690, found here on the base map. Sediment fill in some of the basins was seismically translucent, such as here in the vicinity of the blue star. Also of interest, sub-sediment topographic ridges were seen spanning multiple seismic lines. Figure 8 details line 1657, found here. This portion of line 1657 is taken in the L-shaped flat water bottom region, but this flat water bottom here is interrupted by a topographic ridge indicated by the black star. This ridge is flanked on its east and west side by seismically translucent and seismically opaque sediments. Figure 9 details line 1687, which can be seen here. Rapid increases in topography that form the hills flanking the mouth of Tan Fjord can be seen here in the seismic data, corresponding to the red and yellow stars. According to Kopis et al. 2006, 4 facies dominate the sedimentation of this region. A laminated semi-transparent layer interpreted to be ice-distal glacial marine deposits. This facies can be seen in the vicinity of the blue stars in Figures 5, 7, and 9. A chaotic hummocky facie indicative of ice proximal sedimentation, and it is indicated via white stars in Figures 6, 7, and 9. A laminated hummocky area represented by past sedimentation of fan delta complexes can be seen in Figure 6 in the vicinity of the green star. And finally, an irregular surface coupled with strong reflectors at depth is seen in all seismic sections as horizon 2. This layer is interpreted to be the result of compression and dewatering due to glacial overriding during the last glacier advance episode. Future work includes 2 main areas, processing and interpretation refinements. Processing refinements will focus on eliminating bubble pulses, which are seen in all seismic sections, and in seismic sections that have very shallow water bottoms, the direct wave interferes with them in such a way that they are unable to be interpreted properly. We will work to mitigate these 2 effects to produce higher quality seismic lines and to add their information to our data set. From the interpretation side, we're going to organize all of our data into a 3D model of the region, and we're going to map all faults, terminal moraines, and other significant structures in order to interpret past glacier movements. Thanks for listening.